Okay, students, let us continue the discussion that is going on center of mass. Yesterday, we derived an expression for the force acting on center of mass is equal to F1 plus F2 plus F3, etc. So, when there are a number of individual particles, if there are external forces F1, F2, F3, etc. are acting on the particles, then the center of mass of all these particles will experience a force equal to sum of the forces acting on all the particles. Here, what you should remember is this F1, F2, F3, etc. are all external forces to the system. That means, if there are number of particles in a system, means in a closed system like this, if they collide internally like this, all these forces will become internal forces only. They do not contribute anything to these forces until some force from outside is acting on these particles. From outside some force is acting on the particles, there will be no net force acting on the system. If there are external forces acting F1, F2, F3, etc., then the force on center of mass must be equal to F1 plus F2 plus F3 and so on. So, from this what we can tell, on a system of particles, if there are no external forces on the particles, then the center of mass will not experience any force. That is the main point. And also, when center of mass does not experience any force, acceleration of center of mass is 0. That means, if there is no external force on any system of particles, then net force on the center of mass will be 0. As a result, acceleration of center of mass is 0. In other words, so dVcm by dt is 0 or Vcm is constant. That means, center of mass will move with constant velocity or it may be at rest also. When it will be at rest, Vcm is 0. So, the conclusion from this discussion is, on a system of particles, if there are no external forces, the center of mass will be at rest or moving with the uniform velocity. There will be no acceleration to center of mass. Now, let us see one of the examples for this. There is a body of mass m which is at rest on the floor. On the smooth floor, we are neglecting friction. Unless we specially mention about friction, take it for granted that there is no friction. Now here, if this is if this body suddenly explodes into two fragments like this, these two fragments will travel in opposite directions. Let the masses be m1 and m2. When the mass capital M explodes into two fragments, m1 and m2, they travel in opposite directions. Initially, center of mass is at rest and explosion is an internal reaction. That means, there will be no external force on the system, only due to internal forces it explodes. Therefore, net force on center of mass is 0. As we already discussed, internal forces cannot change the state of rest or of uniform motion or position of center of mass. Here also, when the explosion is an internal force thing, that is why Fcm is 0. So, center of mass is initially at rest, now also at rest. That means, center of mass will be here only. How far these two particles may travel, center of mass is located here only. That is the thing about center of mass. Always be careful about this property. There may be any number of motions internally, but center of mass continues to be at rest or moving with uniform velocity unless some external force acts on the system. Now, let us discuss a little bit more about motion of center of mass. Suppose you project a body at an angle theta to the horizontal, a body at an angle theta to the horizontal with some velocity u. You project a body at an angle theta to the horizontal with some initial velocity u. Now, if it travels in a parabolic path like this and lands at the point P, now what is the path of the center of mass of this parabolic path? Now, let us assume that it explodes into two fragments at the highest point or at some other point. No condition is required for it to explode only at the highest point. Anywhere it can explode. If it explodes somewhere in its path into two fragments, if one fragment travels like this, then automatically the other fragment travels like this, then the center of mass should be here only. If you calculate the center of mass for these two fragments after reaching the earth, for these two fragments, center of mass must be located at the same point when the center of mass is located when the body traveled without exploding or without splitting. That means there will be no effect of this splitting, because the splitting here is an internal reaction. It doesn't have any effect on the center of mass. So the most important point is that if there are explosions of any type, internal explosions of any type like this, center of mass will not have any effect on its motion. One more example we can discuss here. Suppose you throw a Diwali rocket like this. If it goes to some height and by chance if it does not explode, then it comes back like this. That means the center of mass also travels in a straight line downwards. If it does not explode, then the center of mass falls down as the rocket is falling down in the straight line. Now, if it explodes into number of fragments like this, then all these fragments will fall on the ground, but if you calculate center of mass at any position, it will only lie in this on this straight line. It will be along this line only. Because explosion here is an internal reaction, it should not affect the motion of center of mass. So this is also one more example suggesting that internal forces cannot change the state of rest or of uniform motion of center of mass. Now let us briefly discuss various kinds of motion of center of mass. Suppose if you take a body, the body can have linear motion or translatory motion. A body can have translatory motion. When the body is having translatory motion, center of mass will also be in translatory motion. For example, if you take this object, if you move it like this, center of mass also moves in a straight line like this. If the object is moving like this, this is called curvilinear motion. Curvilinear motion is also an example of translatory motion. So if the object is moving in curvilinear motion, which is also a translatory motion, the center of mass also moves in translatory motion. So the point here is, if an object moves in translatory motion, then the center of mass of the body also moves in translatory motion. Suppose if the body is in pure rotation, just like a ceiling fan, if the body is only in pure rotation, then what would be the, if it is only pure rotation, then what would be the nature of motion of center of mass? Suppose if the ceiling fan is rotating, that is an example of pure rotation. In that case, center of mass will be at rest. So in pure rotatory motion, center of mass will always be at rest. In pure translatory motion of the body, center of mass also moves in translatory motion. The other thing is a combination of translational and rotational motion. When the object is executing simultaneously translatory and rotatory motion, then the center of mass will be in translatory motion only. For example, take a solid cylinder or a solid sphere which is rolling without slipping on a rough horizontal surface. When it is rolling without slipping, it is moving like this. When it is moving like this, it is simultaneously rotating around its center of mass and also moving in translatory motion. So it is executing both kinds of motion simultaneously, translational as well as rotational. When the body is executing both translational and rotational motion, the body, center of mass of the body will execute only translatory motion. When a body is executing combination of translational and rotational motion, center of mass will execute only translational motion. So what we can say now, if a body is in pure translational motion, center of mass will be in translational motion. If a body is in pure rotatory motion, center of mass will be at rest. If a body is in a combination of translational and rotational motion, center of mass will be only in translational motion. So this is how the motion of center of mass can be studied. Now let us do some examples or some problems which are generally coming in exams. First of all, let us do this problem. There are two masses on the x-axis. One is 10 kg, another is 20 kg. They are separated by some distance. Two masses, 10 kg and 20 kg, are separated by some distance. Now, if 10 kg body is moved away by 2 centimeters. If the 10 kg body is moved away by 2 centimeters, by how much distance 20 kg body should be moved so that center of mass will be at rest? By how much distance 20 kg body should be moved so that center of mass will be at rest? That means center of mass should not be disturbed. Even though this is moving 2 centimeters, you should move this in such a way that center of mass should be at rest only. It should not be changed. So taking that into condition, we can solve this problem like this. We know that center of mass coordinate is given by m1 x1 plus m2 x2 by m1 plus m2. If there are two bodies, then x center of mass is equal to m1 x1 plus m2 x2 by m1 plus m2. Now let us take differential elements. Dx center of mass is equal to m1 into dx1 plus m2 into dx2 by m1 plus m2. By taking the differentials, we can write this equation like this. When you write like this, what we are saying here, center of mass position should not change. When center of mass position should not change means this must be equal to 0. Dx center of mass means change in center of mass position, which should be 0. If this is 0, what we will get is m1 dx1 plus m2 dx2 is equal to 0. That means m1 dx1 is equal to minus m2 dx2, or m2 dx2 is equal to minus m1 dx1. Because we want dx2, m2 is 20, substitute the values of the masses. 20 into dx2 is change in the position of m2, minus m1 is 10 and displacement of m1 is 2 centimeters towards left. If you take 2 as positive, you can take plus 2 only here, then dx2 will be equal to minus 1. That means minus 1 means 2 we have taken positive, here we got negative for second, means this should be moved 1 centimeters in this direction, so that center of mass will remain at the same position. Again you will have the center of mass where previously it is. Now let us do another problem which is given in IIT once. The problem is two particles A and B initially at rest move towards each other under mutual force of attraction. At the instant when the speed of A is v and the speed of B is 2v, the speed of the center of mass of the system is, options are given to you, A 3v, B v, C is 1.5v, D is 0. So, here what we are given is two particles A and B are there, which are initially at rest. This is A, this is B, both are initially at rest. When both of them are initially at rest, what will be the position of center of mass? Center of mass velocity is always given by m1 v1 plus m2 v2 by m1 plus m2. We know the formula for velocity of center of mass equal to this, and we are given that A and B are initially at rest. Initially at rest means v1 is 0, v2 is 0. Therefore, velocity of center of mass is 0. So, initially center of mass is not moving. Now, what they are saying, they are moving only under the mutual force of attraction. They are moving only under the mutual force of attraction means this is an internal force, it is not an external force. Because of this internal force, there should not be any change in the state of rest or of state of motion of center of mass. Already we discussed number of times. Therefore, VCM equal to 0 should continue because they are moving only under the mutual force of attraction. So, whatever may be the velocities of A and B after some time, the velocity of center of mass continues to be 0. Therefore, answer is D, 0. That is the answer.